field theory modes should be found in their vacuum state at this early time at short wavelengths. And this is, once you take that statement and put it into cosmology, that becomes the Bunch-Davies vacuum. So this is, so inflation takes this belief we have about short wavelength modes and translates, takes that vacuum state and plasters it across the entire observable universe. And this is how, this is what inflation has to say about structure in the universe.
Is this the Bunch-Davies vacuum, the pure state whose partial trace onto a Hubble volume is de Sitter state, something like that?
I think you can say the Adams nodding said that. I mean, it is the most de Sitter invariant.
The pure state of the universe gives us a very simplified view of what we seem to have.
So the Bunch-Davies vacuum is defined within one Hubble distance, but there is the Hawking vacuum state, which is a pure state over the whole universe. Yeah. And when you trace out half of it, the bit outside our Hubble horizon, you get the Bunch-Davies vacuum, which is a mixed state of entropy S.
Well, it's a one-parameter family of states of which the Bunch-Davies vacuum is one. There's the alpha vacuum too. Right? There's a whole class of de Sitter invariant states parameterized by alpha. The Bunch-Davies one is the unique one that looks thermal to an observer.
If you trace out the Hawking state, you get the Bunch-Davies vacuum.
With alpha, so okay, so you don't select it. So you select out alpha 0.
Yeah. There's a number of things I think that, I mean, you can still consider alpha vacuum, but this is a number of ways it's preferred. So anyway, we're taking a belief about the vacuum, a belief that's well ingrained in our ideas about particle physics, and plastering it across the universe. And then in particular, I'm going to come back and point out that we have to adjust our model of inflation, in this case just one parameter, to get the right scale of these perturbations. So you can have large perturbations, you can have small perturbations. We know that we need the scale of the perturbations to be about 10 to the minus 5, and to do that we adjust the inflaton potential to arrive at something that fits. So that's something we do. What else was I going to say here? Oh yeah, and then we collect data, and here we are. We have this, beautiful situation where you have just stunningly tight. When I was a graduate student, and long after that, we had almost no data. And I remember my thesis advisor, Paul Steinhardt, who was heavily involved with the early pioneering papers describing these fluctuations. I remember coming into his, coming back from the Nuffield workshop and just saying, but these astronomers won't tell us what they need. And because they didn't know enough about the universe to know what, whether this was a good idea or not, whether this was could be ruled out by data. But in fact, there's been amazing progress over the last few decades, and there's this amazing, back then it was absolutely laughable, the idea that cosmology could be doing precision science, and here we are with this amazing data set. So we have this situation.
Can I push back on that last point though? That inflation theory predicts those data points. So I'm saying, so I'm going to get to that, but right now I'm just saying we have this amazing data and we have a theory that goes through them. I guess I will say there's features of this that inflation does predict. There's a 6-parameter model that you just put in numbers and run through Boltzmann code and you give that, and I would say inflation predicts half of one of 6 parameters. Everything else is fit.
But another way to look at this, so one of my contributions that I'm especially proud of is working this out for cosmic defect models, and you cannot get these oscillations from cosmic defect models. Right, so what inflation gives you is an idea about the beginning of the universe that allows these oscillations to form.
Right,
so it's more than just a parameter. It's how you might arrive at a situation where And it really is. So this is like a ringing of the universe. When I teach this in a class, I sometimes, well, at some point back in the day when we had overhead projectors, I got a little petri dish with water and put it in the overhead projector. And then if you just tap it, you get these standing waves. And that's basically what this is.
Right.
And then the cosmic defect model is this nonlinear stuff. So like you take the petri dish and you shake it, and you never see, it still has the capability of having standing waves, but you never see them because you're driving it in a random way, and they never settle down into the standing waves. And that was the fundamental thing we learned about the universe.
So that does select out super horizon versus sub-horizon mechanisms for generating things, but like, for example, like if you ask Paul or anyone else who's worked on bouncing scenarios, they would say that they can predict 2 of those numbers, right? The amplitude.
Yeah. So that's the sociology, and but yeah, it's absolutely not the only way to get these, and I'll say that, but now I want to go step by step, and then I think I'm gonna. These are some cluttered slides I'll skip unless things come up in the discussion. And the other thing that happens with inflation is that because you're taking a small patch of the universe and expanding it exponentially, everything has been in causal contact long ago. So this horizon problem is no longer, or feature is no longer there. That was the slide I was supposed to. Okay, so this is sort of the party line. So you in generic pictures of inflation, so this is now we're sort of working on what's your exact picture of inflation, but generic pictures predict essentially zero curvature, which fits with what we have. Here's the point I just made earlier, active versus what I would call passive perturbations. Active perturbations don't give these oscillations, so that's an interesting thing.
It's different Bennett, by the way, I think.
Yeah, I meant to, yeah.
But also Charles, right? Also
Yeah,
I think it's Charles, yeah.
G.
Simple-minded models of inflation give you nearly scale invariant power, and we see that. And this is actually old. I should be quoting Planck here. There's a very interesting, this power with polarization, cross power with polarization. This was one of, so as soon as, within, it seemed like days, it was probably months after I wrote this paper arguing that the oscillations couldn't come from defect models, Neil Turok wrote a paper saying, well, here's how you could get oscillations. So he basically, I don't want to explain the details, but he basically pushed absolutely the limit of active perturbations so he could try to get some oscillations, but they gave different predictions for polarization cross temperature, and so this sort of added, this was an interesting step along the way. And then...
When did that data come? So this is that boomerang that actually showed the anti-correlation? So when did you
I'm thinking particularly about WMAP. I think I'm just. This looks like it's WMAP. Yeah.
This is like a specialty talk.
Yeah. Yeah. So I'm not remembering the history off the top of my head, which is interesting. But the first sign of the peak was some of these balloon experiments. I remember. Anyway, I want to get to more science here. So then people really have a blast, and so all these different inflaton models arrive at different descriptions of the observations, and you can constrain them in this way, and people produce these kind of plots. So it gives a great, if you've worked hard to collect all this great data, here's something you can do with it. You can use it to constrain different inflaton models. And so that's kind of reached some point of technical description of inflation. And now I'm getting into some more worky things. People are already asking what happened before inflation. And I'm going to, and that's related to some of the more contentious topics, including, as people have noticed already in this morning, how will this inflation actually solve tuning problems? It's related to what happened before inflation. It also leads to something called eternal inflation, which has its own controversial status, but I want to give you an idea of what that's like. So next stop is eternal inflation. And I'm actually going to again skip the busy slides and just go here. So here we are rolling down, a scalar field rolling down a potential. It's this rolling that's created this stuff and predicted perturbations. And the thing in the busy slides previous was arguing that the degree that this is rolling in a very classical way. You can estimate the quantum fluctuations here. It's actually set by that same 10 to the minus 5 parameter, interestingly, which is actually a lot more quantum than most things we're used to, but still very classical. And so if this is your picture of inflation, then you're very, it seems very natural to say, well, what happened? So this is the period of rolling that leads to the observations we see. So why not just extrapolate back? That's simple. Like, it's a really simple thing to do. Just extrapolate back. If it's rolling pretty classically here, why not just say, well, what happened before? It was rolling a little bit further up. And I'm going to do that now on my favorite plots here. So here we are, the observable universe. This is the inflation that could impact the observable universe, but now we're assuming inflation kept going earlier on, so we're zooming out. So the blue boxes show the previous slides, and I just keep zooming out. And one of the interesting things that happens is as we zoom out, and this is a very generic result, as the field goes further up the potential, the delta rho over rho quantity actually gets larger. It doesn't affect our universe because we're just living that tiny little blue box at the beginning. We're zooming out, but this, there's a technical result that says this number as we zoom out. So we're just having more and more inflation extending further and further back. This number keeps going up. One of the things I like to point out at this point is that with a logarithmic scale is in scientific notation. That gives you a feeling for how far we're extending back. And we eventually reach a point where the fluctuation is of order 1, which among other things means this thing is not rolling classically anymore. And this is called the self-reproduction regime. It's very far from the universe. I harp on a little bit about the Planck length, which I don't want to spend time doing. But what we're saying now is that because this rolling is very quantum, there's a substantial probability of fluctuating up the hill. And that, combined with the fact that you're expanding exponentially, means that in a global sense, again, skip some things. In a global sense, the inflation never ends. And so here's how I've tried to depict that. So this is the self-reproduction regime, heavily fluctuating up the potential, exponentially expanding. In fact, a given region will always eventually fluctuate down and start rolling classically. But the point is that around it, there'll be more exponential expansion, creating more inflation. And so exponential expansion here, classically rolling in some patch. We're zooming out. So this is exponentially expanding, so is the self-reproduction regime. So as we're zooming out, the next pocket, which I'd expect to be about the same size as this, is produced at a new time. I've zoomed out so the pocket looks smaller on this plot. Yeah.
I'm afraid I have to admit I'm completely lost.
So,
I have no idea what some is.
so I'm mapping out.
The previous ones to the few previous slides.
Yeah,
Just
I'm
like flip
So let me go to this. So we've extrapolated. So here's a little region of rolling scalar field that inflation maps onto the cosmos, onto observables in the cosmos.
What are we, I mean, is this now at what point in your universe? Or
This is the thing that,
So here's this favorite plot of mine.
Yeah.
Here we are today. This rolling, as I showed a few slides back, is describing the evolution here.
Okay.
And then we're extrapolating back and saying, well, if all that happened beforehand is that you were rolling further up the hill. So now we ask, what happened before this?
Back in time when you roll out the hill.
Yeah, exactly. That's what I'm doing.
How much does this depend on just extrapolating that quadratic differential, I guess?
This happens for other potentials, but I'm showing a simple one.
All other potentials, some other potentials?
Almost all other potentials. So how did that help something?
Yeah.
So now I'm trying to. Okay. So now I'm saying we've done this extrapolation. We've reached a point where we're now no longer justified in assuming this is classical rolling. So I've done some estimation of the quantum fluctuations. I've not hacked through it. I have 10 minutes left in my talk, so I'm not. We could talk about that, but I've done some estimate of the quantum fluctuations and found as I get further up, they dominate, and therefore this idea that I'm simply rolling down no longer applies. I can fluctuate up, and whereas one little patch is going to also have a chance of fluctuating down and eventually start rolling classically. While it's up there, it's producing more volume. So there's it's called the self-reproduction regime for a reason. It's understood to keep producing inflating regions of the universe, even as bits start rolling down. So now I'm trying to imagine what that means in a picture by mapping out. So here's a region of the universe that's in the self